That's bright. Good morning. Now I can hardly see you against the light. Great pleasure to be here and to opening up the conference with the pre-conference tutorials. I think last year's conference, in their wisdom, decided they didn't need an Rcpp tutorial, so it's extremely gratifying to see such a large room and so many of you coming out, because seemingly there is interest for it. So that's pretty awesome. I've just done this again last week for 2 full days in Zurich. Today we only have 3 hours. So I think I'm mostly going to give you sort of a, why, and some usage examples that hopefully will give you enough material to get started and get a flair of what one can do and where to find more information. These are meant to be hands-on tutorials, and I tend to drift too often into just plain lecture style. It's also, with Rcpp, a little tricky to get, the compiler set up if you've never used it and sort of things like that. So with very generous and kind help from RStudio, if you're not set up on your machine, there's a server in the cloud for us at that address. It's a bit tricky for all of us to ad hoc coordinate who uses which login, but there's 400 of them. So you just have to be really good as a random number generator and pick a UID that nobody else is using if you use that. Or if you happen to be set up on your machine, which really isn't that difficult thanks to the tooling, then use your own. But if you can't, try that. That's Harper's Ferry with a hyphen, rstudio.com. Usernames 101 to 500, password RStudio with a capital R and a capital S. And if you see that, do take a picture, tweet it. If you see them in the hall, tell them thank you, particularly to Nathan Stevens for setting up the machine. That was really helpful. I will, on occasion, hop out, and where did it go? So I have one here as well. I think I'm, as you can there, so I'm 345. So if you log in as user 345, I'm gone, so don't do that. Or I fall back to my laptop. We'll all make do. So, and or worst case, if you're not set up, but your neighbor is, maybe just take the seat next to you and then sort of look at things. So all good with that, I hope. So once again, thanks to RStudio for setting that up. So overview, what are we going to do in the 3 hours that we have, and the before the break, after the break, not quite sure when that'll occur. So in essence, I want to talk a little bit about why, then sort of briefly how. The how, of course, we can spend days on, as I just did last week, as well as the what. So we'll mostly just look at concrete examples that work, things that are all out there that you can download to your machine and should be able to replicate in most cases. Towards the very end, we come to a usage example where we're working with an external library, and there it gets a bit more to the it depends thing. That works really well on the type of machines that I use, Unix, Linux machines. It's a little trickier on Windows. You just need to put the effort in to build those libraries on your machines too. It's all doable. So, big topic, sort of why R, right? Preaching to the choir. We're all here for a couple of days, celebrating R, learning R, using R. An example I've been running with for a couple of years because it's pretty nifty, I find, and I think you'll see as well. So we're all familiar with sort of those 3 lines, right? We don't even have to load data. There are sample data sets that come with R that we can study. Faithful is the name of a geyser in one of the US national parks, and this is times between eruptions. So we're subsetting a single column of a data frame named faithful. We now have a vector in XX, and we're just calling one of the built-in statistics functions density to get ourselves a density estimate. We don't even look at the density estimate, what comes out. We're just taking this thing called fit, and we're sticking it into plot. And just see if that worked or didn't work. The pointer definitely works as a pointer. Does it advance too? It advances, beautiful. And when you do that, default parameters, default data set, no randomization whatsoever, we should all be getting this plot. It has some descriptives, so apparently sampled the density or estimated the density based on 272 observations. A default bandwidth is taken. We're not going to preoccupy ourselves now with which method and all the rest of it, and there's sort of some labeling because we didn't override those defaults. So it's definitely good enough as a first step, and we can do that in 3 lines. That's pretty good, but truth be told, you can do that with other languages too. I mean, probably by now you get a density estimating library in Python, I presume. But where R shines is something like this. So I didn't write this up. I took this from Greg Snow's post to R help a couple of years ago when there was a similar discussion about why R and why is this good. So this is a little harder, but the slide will be in the slide deck. The slide deck always ends up on my website, so you can recover this. And if you go through line by line and analyze what's happening, it's not that incomprehensible, even though it's relatively dense code. So same thing, we start assigning the data set we're working with. As in the previous example, we're fitting a first density, but now, because we're fitting density several times here, we're just assigning it to a variable fit1. And we will be making use of fit1 twice. The first one is in the actual core Monte Carlo replication, or bootstrap replication, if you wish, inside this replicate call. Replicate is another base R function that's a little hidden and doesn't always get that much limelight. It basically just said 10,000 times, do me this. And as with any R code block, the value of the code block is what gets finally assigned. So what we're doing here is we're shuffling the original data set with replacement. We're then recalculating the density, parameterized with the minimum and maximum of this first initial fit so that we have a proper grid on which to operate, and we're extracting just the Y column, the estimated density, because the grid on which we fit we held constant over the 10,000 replications. Having stored these 10,000 Y vectors in fit2, we then invoke the quantile function to get 2.5% or 97.5% coverage in the tails out of this, and we plot this we then plot the original fit as before, but now we're parameterizing it to the range of this distribution that we computed so that that doesn't run out of the picture. And we augment the picture with my server died at home, and the replacement server is not well configured, so I get a lot of cron messages. So this sadly will happen a bit more the next 3 hours. So for as long as I remain on the internet, so bear with me. And then we're using Polygon to visualize the fit3 quantiles that we contributed and overdraw again line 1. And the end result is this. This is now the same fit as on the first plot in black in the middle, but in gray around it we have from 10,000 draws the 2.5% to 97.5% uncertainty coverage around that estimate. So that's pretty nifty. A page of code, and we now have uncertainty estimates around our non-parametric fit from that original example. And that's sort of hard to do in a lot of other languages in just a page. So that's why we like R. It also in some form opens the door to something that we often do with Rcpp. There was sampling in there. There was implicitly a loop in there, so we didn't write a for loop. The replicate did that for us, but that's sort of why R. We can work interactively. We can access data sets. We can estimate on the data sets, visualize the results. We can access, retrieve, and generate data and summarize and report all of this. I didn't do this here. We just stuck with this plot, but I could make the plot pretty and generate PDF outputs, HTML outputs. So it's really good. That's just why R is so popular. We like it as a language for statistical computing. But what if we want to go beyond R and want to extend it? That has always worked. I started working with this in the 90s. The Writing R Extensions manual was already then what you sort of went to, and it went through how to extend R with C and with Fortran. Around that time, I think in the year 2000, Kurt put a minimal test package somewhere onto a dark corner of CRAN that had the minimum of C++. Because there's C, we can also do C++. But all that was sort of a little tedious. And then, of course, in those days, we all thought that the only next language we'll all use would be Java. And then for one reason or another, things changed, and now we don't like Java all that much, but it's still there, and it's useful for a lot of things, and Simon still supports the R-Java package, of course. Another view of sort of why R. I like this a lot sort of at a historical perspective. These are all book titles by John Chambers, either by himself or with co-authors. Trevor Hasty here, Becker and Wilkes there. The first one goes back sort of to the days before R and S, but I'll get to that in just a second as well. That's from '77, basically sort of pondering, well, you know, how do we use these newfangled computers to do data analysis? And that had a lot to do with interfacing Fortran. S wasn't really there, and then at the end of the 80s, S existed, or actually the remake S existed, because there's a new in there, the new S language. But that's sort of prehistoric for us. What we're still using today, however, is described in the next one, White, the White book, early 90s. So that introduced S3 classes, the tilde notation for formulas, LM, things like that. Couple years later, the Green book introduced a lot more formalism, S4 classes. Had the wonderful title Programming with Data. So the notion now that we do, you know, bigger and better things for which we need more structure, say S4, as they use a lot in Bioconductor, is there. And then the next one was actually the first one that I really read of all of these, which came out about a decade ago. This one's really good because it recaps a lot of the history of the why, how the design evolved, and it's the first one, as you know, that has R in the title. By that time, you know, John Chambers had long become an R core member. He had contributed to R, and now software for data analysis is actually about R, even though it's only in the subtitle. And then this one's fantastic. That's from last year. I like this one a lot, and now it's about extending R. And that is, of course, a topic dear to my heart because Rcpp has been focused on extending R for quite some time, and that book too ends on quite a bit of Rcpp. So the previous books, those the 2008, the final two chapters are about interfaces. And they discuss this extending. So why do we do this, right? And he says sort of, at the core of R, again, is the C language. R is built with C and a lot of C code. And when you have the C language, you can generally extend with C or make it callable from C, sort of both directions. But that's not a gimme. C code is a serious step, added dangers, substantial extra programming, possibly debugging. You should be motivated to do that. You need a reason. So I'm highlighting some of these things again. Sort of danger, work, debugging. So I like lining them up sort of sports score style. So then you could argue it's 4 goals versus 3. And it's almost more for the against. But then again, the in favor have sort of so much weight that we often overcome that. And among these, speed is often good enough a reason in and by itself. We just need to make things faster. But it also allows us sometimes to do things with compiled code that we couldn't do beforehand. So new and trusted computations, and object references is good too. Sometimes it allows you to access things without having to copy them full and sort of things like that. So again, why extend R? Speed, definitely. New things, references. This goes back to, or it predates, this 1977 book that was on the slide with the 6 book covers. So this one's really, really charming. It says 5/5/1976. So this was a bunch of staff scientists at Bell Labs in New Jersey thinking about how to create systems to compute with data. Back then in the day, computing meant accessing Fortran routines that people had written, because scientific computing, research computing, invariably at the time was Fortran. C had sort of barely started to exist also at Bell Labs. C++ hadn't. So they were then thinking about a core routine ABC that would get accessed with the routine XABC, providing the interface. And the rest of the sketch is about, you know, how memory would be laid out, because that was the closest they were getting at the time to thinking about variable passing. I mean, it was all a bit more bare bones. But I saw this first not quite 10 years ago. John had used this in a speech in a presentation at Stanford. I think that he gave a week before Romain and I were out there visiting him. We were there for another reason, but he made time for us, and I quite liked that. And he had sort of, you know, very friendly and gracious words to say about Rcpp, because the idea always was, give us access to inner cores, to trusted subroutines, but let the analyst access them from the outside. And in a way, you can see that it took this long to really get to that, get this vision materialized, but we have that now. So he also became an early contributor to Rcpp, so it's all good. I think now I went the wrong way. So again, we work with R and we extend R because it gives us sort of a two-punch. We get compiled code, we get high performance, we get access to trusted libraries to extend R, to do new things, and at the same time we can still interactively work with R the way we like this as data analysis. So it's a good place to be. That's the motivation why we do what we do. So, you know, now we settled we like R, we want to extend R, but then why on earth would we use C++? So if you do what we all do, you ponder a really sort of difficult question, one to say sort of, why this, why that? And the first thing, of course, is to go to Google. And if you punch in why C++ into Google, it comes back with a summary page, and then in the finer print, you know, 30 million further results are available for you. Of course, we can't read all of those. Often the first link then goes to Wikipedia. That's a hyperlink too if you access the PDF. Once I upload them, or an older version of this, which are uploaded. And that's the usual sort of mouthful. It's statically typed. That means it's a compiled language in which you have to declare your types. If you want to assign the value 3.1415 and so on to a variable, you have to declare that variable double. It's a floating point number, so you can't assign it to an integer. You also can't assign it to a char or a different variable type. So statically typed, it's free form, meaning you're not constrained in how you're setting your programs up. Multi-paradigm, it's not out of one use case, science discipline, industry, or whatever. Compiled, making it machine code fast. It's very important too. There's no intermediate layer there. C++ was designed to not leave basically room for another even faster language in between. When you use C++, you generally don't have to go down to assembler. I think I have another slide on that, or I'll just mention it. General purpose, again, sort of multi-paradigm, general purpose, powerful programming language that's really widely used. AT&T built it for themselves to manage the software controlling the phone systems. Even then, these software projects were in excess of 100,000 lines, and they felt they needed something more manageable than just C code. So there's a bit more structure in C++. It's still used for these and other things, industrial strengths, vendor independent, still evolving, very important. You may have heard about C++ 11, C++ 14, C++ 17. The language has sort of awoken from a bit of a slumber in which it was when Java and C# were sort of ascending 10 years ago, and then sort of has responded strongly. So it's very much alive. It's very widely used in other research areas, in other science areas. That means we have access to good libraries to use them, and similarly, because it's not an obscure new language, there's extensive tooling support, there's books, tutorials, profilers, so you can work with it well enough. So how do you get started with C++? A set of books I always liked were by Scott Myers, who's an author, consultant, trainer, and the first of the ones that he wrote was Effective C++, great book, and in the first edition it had 50 sort of chapters, short topics, short discussions of particular aspects you need to know when learning C++. I think he had positioned the book sort of as not your first programming book. It helped if you had seen C or Pascal or something else, or even R before. The first of these 50 topics is sort of actually answers why C++. And he very eloquently and convincingly makes the point it's good because it's a menu. It's a federation of languages. It's actually 4 languages in one, and you don't have to use all 4. When I learned C++ as a grad student, sort of mostly brute force, self-taught, I was always joking that I used C++. So I was coming from C, and I was using just enough features of C++ to make C more bearable without getting into a lot of sort of heavier duty C++ then. So the first language of the 4 per Myers really is the same as C. If you know C, you're basically ready for C++ because you can just sort of continue as you've programmed before. The next one is that it has object orientation. And object orientation is, of course, a big topic for computer scientists, for software engineers. The meaning is a little loaded. How we do object orientation in R is a little different. So, that can go on forever debating that. So I just mentioned it has object orientation. It's a little different. Then one thing that's very unique to C++ that other languages haven't really copied because it's hard to implement is it's templated. So, which means you can do what is called template metaprogramming, which means that programs get written while the compiler builds your binary. So actual processing time is spent at compilation time. So you amortize it in such a way that the hard work is done at the beginning. It makes your compilation times longer. It makes the compilation slower. It takes longer to compile, but it makes the runtime faster. So that's something other languages can't really do, and it's one of the tricks used inside of Rcpp as well. But as a user, again, that's not something we would commonly deploy. And then finally, showing a bit of the age of the book, the standard template library was outside of the core of the language, and you could now argue that it's really become part of the language. It started as an external contribution by someone, I think he was first at HP in Agilent or something, and then moved, but it's very common, and it's the thing that gives us vectors, lists, strings, lots of core data types, and those have passed the test of time. Now, years after Maya has written that, we could actually argue that it's now 5 languages because C++ 11 and 14 give us another set of expressive options to write yet again in a more concise, often functional style as well, sort of something that we like from R as well. So that's why C++ and what C++ is. So again, sort of to summarize, it's a super mature current language, but it's current because it gets updated. It has a really strong performance focus. These language standards people have meetings several times a year. A couple of years ago they were in Chicago and sort of the luminaries were there, and Strustrup, the founder, basically said, why C++? And you waved a smartphone. Because one thing that matters is that you want performance not only in raw speed, flops, how fast can you solve a problem, but also how efficiently. And this flops per energy unit, per watt, is pretty good. So it's a good language for both data centers, for large computers, less cooling, as well as for smartphones, because your battery will last longer, because it's efficient. The way it's implemented, it means that even though you have this menu of 5 different languages to choose from, if there are features that you don't use, they don't slow your program down. That's also a bit different to Java and C#, because you have the intermediate layer in there that can hog you down. So leave no room for something else. It's abstract and high level, so you can reason the way you can do in R. And yeah, C++ 11 and 14 are exciting, and all sort of these build complexities we're mostly shielded, and I'll show you that in a bit. So quick interlude again. So chapters 10 and 11 from the books that I mentioned, C and Fortran interfaces, interfaces to other systems. This one builds on that and makes it a bit more concrete. The Extending R book has a package on CRAN that goes along with it called XR, Extending R. And XR is used by XR Python, XR Julia, who have minimal examples of how to extend R towards those languages. Because what John said in this book basically was 3 really important things. 2, that we've all heard before, sort of that comes up in discussions with other experienced users. When you're working in R, everything, really in your session, everything that you're working with, a data object, so a variable, a function, environment, everything really is an object, and we can get hold of those objects. And everything that happens in R and changes the state of these objects is a function call. Everything is a function call. And then the new thing that just comes out for the first time in this book, interfaces to other software are a part of R. That's a really strong statement, because it gets us back to this sort of why R, and is it worth to work with 2 languages? Is there cognitive overload? You know, does it make our programming job harder when we have to get from one language to another? And John basically sort of outright says at the beginning of the book, interfaces really are part of R. If something is solved really, really well in another system, we should just use that and access it and build good interfaces. And a lot of that book then is about how to build interfaces. I think he calls that programming in the small to programming in the large. And programming in the large is sort of the heavier duty stuff, and he then talks Rcpp as well. So good book. I enjoyed that one very much as well. So it was a little dry. I just sort of tried to motivate things, and just to make things a little easier to digest, here's just something that I had collected over the years and had sort of somewhere on my hard disk. So this is from many years ago from a unit at Harvard that has now been renamed. So this is quantitative computing support for the social sciences, and you know they were early fans. Speed of C++ with the ease and clarity of R. So that's well put. That's sort of what we're shooting for. And they thanked me and forgot Roman, but then he liked it, so his picture is there too. Peter was a PhD student for a couple of times. Now he's postdocing in the States, so sort of, you know, you can't put this in the New York Times, but we can say this here, holy shit, that's fast. Exactly. So that's sort of what we're aiming for. Pat claimed that he got something 750 times faster. That's sort of very good for him. I don't manage that myself every now and so often. Maybe my C++ is not as good, or maybe my R isn't as bad, or sort of something like that. Sort of a gap that wide is sort of good, but yeah. I don't know. Maybe when you do this old saw of growing your vector in a loop or something, you need to copy it around. You need to do that all the time. I seem to have a very large weight on Australians and New Zealanders. So there's another, well, he's in hiding in London now. So that's, you know, when it makes dealing with sort of C stuff much easier from C++. So Rich liked that too. Roman quoted Hadley when Hadley was keynoting 3 years ago at the first Earl conference. Hadley lists sort of Rcpp as one of the 3 things that changed how he writes stuff. So because of him, Rcpp is everywhere because he uses it a lot. So that was good. And then Carl is a bioinformatics professor, so he does genetics, author of the QTL package. He likes it too. And exactly, Bob says it's the bee's knees. And then I think I have a slide from Colin, who sits there somewhere in the back in there, which he uses in his book, which, as he's a good guy, is open source and in Markdown somewhere on GitHub too. This is, this is properly done. It's on a log-log scale. So what looks like something that could be smoothed to a straight or approximated by a straight line really is exponential growth. And both of them are growing. Our Java is still growing, but there's a bit There's a bit of a gap between the 1,000 and 10,000. I think that was probably done last summer or so. So the numbers are now a bit higher, but the trend lines are the same. There are other languages too. So there is an old package that interfaces R, which way around? I don't remember quite now. That may be calling R from Python. I mean, we have them for both ways, but they're two different ones. And V8 is Jerome's very fine program for working in the browser with JavaScript. A JavaScript engine. And this was a couple of months ago when Gabor gave a webinar on the outstanding, you should use this, RHub, which is up and running. You can use it and build your packages there, and he was just going through how one can use RHub for debugging. And he was setting something up where he's forcing himself an error. And yeah, he was just saying it's much easier to make an error when you're not using Rcpp, meaning that if you're with Rcpp, sort of you avoid a couple of other things. So that was the suite of tweets, sort of more lighthearted, but so summing up this whole motivation section, sort of it's still easy enough to learn, and we'll get to concrete examples in a bit. It's easy enough to use as well, because how things are set up is that eventually everything that we're doing calls out to R command build, R command install, R command check, and it's R itself that keeps track of where your compiler is, how to call the compiler, and all those things. So the actual load and requirements for working with Rcpp are no different from working with any other compiled language. If you had decided to extend R with C, you would have the exact same need. You're mostly done on a Mac and on Linux, and on Windows you may have to install RTools, the set that gives you the G++ compiler, or for C the GCC compiler, and the C++ compiler comes with it. So no extra baggage, and R mostly takes care of it. It's expressive. We'll see this in a bit. So we can use vectorized expressions that look like vectorized R expressions, something that C++ by itself doesn't have. And that's some of this template. Metaprogramming, the thing that everything is an object in R, it's a big deal, because everything is an object, and all these objects behind the scenes are represented by R really in the same data type. It's what's called a union data type, sort of a wraparound thing, and we get to that from C++, meaning we get to all these things. So we get vectors, matrices, lists, S3, S4, reference classes, environments, functions. It's good. And yeah, so speed gains, and of course, if you need to talk to other systems, scientific computing libraries, database interfaces that you get in a compiled library, whatever, all that is easily doable. This I update every couple of months for these types of presentations. I think here I used it from something that I did earlier in the month, so it's a bit behind now. We're now at sort of 10,070, which is really, really stunning. It's sort of hard to believe how much it has taken off in the last couple of years. It's really humbling. If you can see, there's a fainter blue line behind it. When I started putting this chart together, they were actually in the way the scaling works, they were then in parallel. Now they're a bit separated. That's the right-hand side scale, and it's the percentage of packages on CRAN using Rcpp. So we're bubbling up on 10%, which is pretty good. We're at sort of we're just under 1,100, and CRAN itself is just under 11,000. Am I missing one? Yeah, there was a PageRank slide in between that I seem to have taken out, borrowed from Andy DeVries's PageRank package, so that's not there. So ignore the chart. PageRank is sort of cool too. He surprised me quite a bit there in 2 years ago at useR, sort of showing that we were per PageRank the most central node. This is something new. There was sort of a question that I had that I couldn't easily answer with a lot of effort and web scraping, so I didn't. So, we know what the number of packages on CRAN is. CRAN actually prints that on a summary page. So currently, again, this is sort of from a couple of days ago, so now we're maybe at 10,950 or sort of something. But with R34 and later, there's a new helper function, CRAN package.db, which returns one really chunky data frame, 65 columns. That data frame contains every mandatory field in the description file, and its contents, as well as a couple of computed and parsed things. So each row is a CRAN package, and there is, for example, a field in there, depends, imports, suggests, and because it's a data frame, we have limits of what we can put in there. The list of packages a package depends upon, or also the reverse depends, I think. It's just in there as a text vector, so you have to, interesting. So one of you is hacking into my computer. Tis, 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 tis. But among these 65, some of the computed fields that CRAN needs for the operation, for example, is needs compilation. And needs compilation is basically a proxy or just an indication I can now pick up as to whether the package in question has a source directory. So I was always wondering how many of the CRAN packages actually contain compiled code. And now we know. So for that day when I did the query, it was 2,919 out of 10,900. So, you know, somewhere between 25 and 30%. Bit more than every fourth. It's reasonable. Shared that number with someone from our core yesterday, and they were actually kind of going, sort of, that's kind of too high, they said. You know, R itself should be fast, so we shouldn't need compiled code all that often. And the question that I really had was, you know, what's the ratio of these two, this number? How many of the packages have opted to go with compiled code, which is sort of more work than a straight up R package? Not necessarily by much, but a bit. How many of those use Rcpp? And for a few weeks now, we can answer that, so that's a bit more than a third. So that I found quite interesting too, and that's actually, that's a pretty broad reach, so it's pretty good. So that concludes the motivation section. So now we're getting to something a bit more hands-on and actual examples. So let's talk about the why do we do this? Speed. Yeah, the examples in here, actually maybe I should have put that on an opening slide earlier, are all available to, I just copied them all out. I had sort of one catch-all repo with examples from several talks, but because I gave a 2-day one last week, so a superset of the examples we use here is in this repo. That's if you just sort them or if you write that down, then you have that. And for example, what I'm looking at now, so you can clone that. So what we're looking at now is called straight or curly. There's two of them there, so that just for completeness. So this was a bit of an aw shucks. So that also goes back to a discussion on the mailing list a couple of years ago. I think that may have been around the time that Redford Neal started with PQR and made this observation that, you know, curly braces actually evaluate faster than round parents. And Christian Robert, who's a Bayesian in Paris, cooked up this example. And basically, what do F to K do? There are 5 different implementations of doing the same thing big N times. So here, for the purposes of the benchmark that follows, we said big N to 10 to the power of 5. And it's not doing anything meaningful because the number that we're computing is doesn't really matter, but we're basically going big N time through a loop, and we're assigning to the variable x the ratio of 1 over 1 plus x. And as you can see on the right, there's at least 5 different ways of writing this, and then the question then is, if we write our R code this way, sort of, does this matter? Is there a performance difference? And the interesting bit, of course, is that when something like this gets written and you revisit it a couple of years later, the answers aren't necessarily the same, because sometimes wasn't implemented optimally, and then they change and your benchmarks change a little. But so what happens when we run this here? And sort of we're introducing and passing the R benchmark package. Super useful because you can just call its main function benchmark with a number of function calls. It's a ... so it takes 1, 2, or as in this case 5. Here they're all functions taking 2 arguments. The default argument is actually redundant because it's in there too. And order relative means the results will come back in a sorted manner. And then on this laptop, very recently, it gives us this. Basically meaning that, 100 replications, so 100 experiments of these 10,000 draws take sort of roughly half a second, 555 milliseconds to 597. So these two are are essentially indistinguishable because there's a bit of measurement fuzz when you're doing benchmarking on a system that's, because it's a computer not entirely idle and always doing something else. This is sort of pretty close, and you could argue that it's the same. There's a bit of a gap here, but who really sort of cares in the grand scheme of things about 40 milliseconds? And then this one's a little slower, and then you can go back and sort of see, well, which one was H? Well, it turns out that if you're writing it the math way with an exponentiation operator, somehow it takes R a little longer to compute that. But I kind of just looked at that, and I was sort of in the Rcpp mood and kind of figured, who really cares? Because, if we're really caring about sort of an expression with these curlies and we wanted it faster, it's a loop. So let's just write the loop faster because it's conceptually a really simple thing. It was a function of 2 arguments, a counter and an initial value. The counter here we set to 10,000, the initial value we set to 1 because it doesn't really matter. And then, of course, we just loop over it and we assign 1 over 1 plus x and do that. So here we're just sticking this as a constant string into something called CPP function, which we'll formally introduce in a bit. And when we run this thing, now all of a sudden, these are still somewhere between, a second ago was 550 to 590 to 700. It's still sort of in the ballpark, but our new function is basically at 1/7 of that time. So, and that was my sort of, oh shucks, I don't really care that he can measure a difference between encoding blocks with curly braces instead of round parents, the way we would normally do it for a mathematical expression, because the big thing is that these are basically all equivalent and much slower than what we would do in Rcpp. And the reasoning with Rcpp can be, this simple. You just get a 4-liner executed just that way, but more about CPP function in a bit. That was speed example 1. The other super classic speed example is implementation of this recurrence. This is known as the Fibonacci sequence. A Fibonacci is defined as, for all values large enough, the sum of the 2 preceding values with a stopping condition provided by returning the same value when the argument is less than 2. You can Google this. It's actually great fun to Google this and comparison of implementation, analysis of the algorithm. And there's 2 differences. You can define it with starting with 0 or starting with 1. I took the one here that starts with 0. So we're basically implicitly saying that n is always non-negative, 0 or greater. Looks nice. Makes me feel all grad school that I can use LaTeX for an equation on 2 lines. And the nice thing is you can sort of look at that. We sort of still all understand what it means with enough coffee, and the code that's behind it in a naive implementation looks basically the same. I say it's sort of naive implementation because this one, and I'll get to that in a second, has a particular cost structure in computing, so it's an over-analyzed example in computer science because the normal way we do this here, because it's a recursive sequence, we calculate it as a recursion. And there's lots of other ways that you can do that, but if for now we're staying with the recursion, which is the most natural representation of what we wrote as a formula, then the performance is terrible. And that's sort of okay, because we've spent all this time motivating why we use R and for what R is good. And there's no free lunch in life. There's sort of always certain things where something bites. R is a fantastically general language where you can do tricks you can't do in other languages because it's made for working with data. One thing it does not do perfectly well is calling functions, when a function gets called, it needs to keep its state. Certain things are, sort of put on stack and heap and other places. Basically, there's overhead. It's expensive. And we know that, so that's just how R works. So when you know that and reason about a function that's implemented with recursion, you know this won't work all that great. But that's sort of speed. And the first concern is just correctness. So here we just write it, and then we look at it. S apply from 0 to 10, called on F, gives 0 to 55. Passes the smell test, because we had said for arguments less than 2, we get the argument back. So for 0, we get 0. For 1, we get 1. For all other arguments, we get the sum of the two preceding ones. So here we get 1 plus 0 is 1. Here we get 1 plus 1, and so on. So that's the thing. But how does it perform? Not well. If I go in and just call it with f of 10, so f of 10 has to be the sum of f of 9 and f of 8. So for f of 9, it has to compute 8 and 7. The thing is, it's worse than exponential, because at every point it sort of forgets that it needs this point in the other branches too, and it just recomputes and recomputes all over. So you see that when we go from f of 10 to f of 15, we increase the load by just 50%, but the cost is a factor of more than 10. Instead of 11 milliseconds, we now spend 115 milliseconds, so 10.5 times as much. Going from 15 to 20, same thing again. So if anything, this gap was a little smaller, this is a bit larger, so here we have a ratio of 12 times rather than 10 and a half. So it's not good. But again, it's trade-offs. So R is an interpreted language. It doesn't do function calls all that well. C++ is a compiled language. Things it does really, really well include function calls. So something like that is cheap here. We get the exact same sort of elegant logic of not having to torture our brain to come up with really, really clever and possibly buggy algorithms. We take the formula the way it's on the paper. We just say, if it's less than 2, return n. Otherwise, return me the sum. Now I've called it G because F was already taken. Those 4 lines with the 2 curlies are valid C and C++ code. It's not yet a function because there would maybe be an include file above or whatever, but that's sort of how we would write it as pseudocode. And going from pseudocode for C++ to an actual implementation in Rcpp is this simple. It's a 3-liner, or if you wish, it's a 3-liner here, so it fits on the slide. You can actually, join those 3 lines together. It's a 1-liner. We call CPP function, again, which gets introduced in a second. CPP function is set up in such a way that the function identifier hiding in the string that you submit will become the function identifier of the object that you call from R. It's an extra nifty feature. So now we had our function f, we wrote ourselves a function g that does the same thing but in C++. We do what we did before, we're calling it with argument 0 to 10 to make sure we get the same results. They are the same. Often I do an all equal of the 2 results because it's really important when we strive for performance that we don't lose correctness. So by all means, let's write solutions in R first, then write faster ones. And so on. What happens when we stick the 2 of them together? So now it's just one call to the benchmark helper function as before. By default, it runs 100 replications. I order by relative performance. I suppress columns 5 to 7. That's just sort of the other columns that you get back from sys time. Doesn't fit on the slides, and it's not that important. The ones we really care about is this. So F20, it was about the same on the other slide when we did 10, 15, and 20. It's a bit more than a second, but when we do it in compiled code, it's barely noticeable. It's 8 millis, basically no time. And here we have a gap of 150, which is pretty good, looks pretty impressive, but again, sort of keep that in mind. The horse race that we set up between C++ and R handicapped R because it's function calling. But it reminds us that function calling repeatedly is also something worth doing with the compiled language, and it doesn't have to be Doesn't have to be complicated. I should say at this point that it's worth also applauding Rcore for what they're doing with the language. I don't quite have it from the top of my head, but it's all on the web server. When I started using this example in slides, on possibly older computers, slower computers, so these numbers may well have been different for elapsed time, but what's important is generally for the same argument, the gap has closed. So R does these things now a little more efficiently. I mean, not so much so that we would stop going to C++, but it's, they're making the language better too, which is pretty good. But then speed is really two things. It's how fast you get your answer once you've solved the problem. The other part of speed is how long does it take you to get there. And we like R because it's expressive. We can write code relatively quickly. Writing code in C and C++ is not necessarily quick. The slide that I showed you earlier with the quote from Jem Chambers, additional work, possible debugging, you should be motivated. So it's good to have a proper setup in which you can do these things. And that's the other point where Rcpp sort of is helpful. Not only does it make these things possible, it makes it easy with these tools such as CPP functions. So that's good. And beyond that, if you're reasonably new to that, or even if you've started and done that, have done this for a while, it generally pays back over the longer term when you plan to do this for quite some time to get familiar with editors or environments that help with the tooling. So RStudio, the IDE has gotten much better now. It can help you write C++ code too when you're editing. It gives you member functions, things like that. When you build the package, it analyzes the error message. So that's good. But you don't have to use RStudio. Some people, like C-Line, Eclipse, Emacs, what have you. But it's worth investing in proper tooling. So what next? This I carried over from the course from last week, so I'm just going to put the slides up and go through really, really quickly, because why not? I mean, it's an Rcpp tutorial, so just what's really different between R and C++? So first thing is it's a compiled language, so this would be a freestanding C++ program that we could compile and link. It's not an interpreted language. That's the same thing, but using a different input-output facility. So C++ gave us this, but it also supports what C had before on the previous slide. So we have different stream outputs. It still needs to be compiled. How does one compile? Well, if you're on a system with G++, G++ -O takes a source file and generates the output that follows the O flag. The next thing that may come in that you may have to become familiar with when you're debugging this is compiled code can access code from other components, from libraries, via a step called linking. I have a minimal freestanding example here that uses, the rmath library, which is something that comes as source code with the R source code and can be built when you build R. I'm not quite sure if that's ever done for the Windows builds. We do this for the Debian and Ubuntu builds, so this one would run there. So we have now a small program that doesn't just print hello world to the screen, but uses the same implementation that's used in R for the qnorm function to find the value of the 0.95 quantile of a standard normal. And I always forget this. This means extra tail position, but not logs or something. It basically is the default for trues and false. We can ignore this for a second. If you run this as a small example, the way you would do this, on your Linux computer or maybe on your lab's shared Linux computer, is you sometimes have to give a -i argument to find header files that define other functions. Here we're doing it as a two-step, the way R does things. So we're compiling only the C++ source code into an object file, and in the second step we're linking this object file into the output qnorm using rmath, using the object file we just created and the rmath library from this location. So just to show you how something like this works and the things that you have to keep track of. But for R, package building, rcommand does all of that for us. And these paths may look different on a Mac and on Windows and on a Linux box, but they're functionally equivalent, and everything happens with these minus capital I, minus capital L, minus lowercase l flags. So if something goes wrong, you want to look at the messages that the computer gives you, what it tried, and then you have to reason why that may have been wrong. Again, it's statically typed, so in R we can say XB314 followed by X assign foo. That works. So something that started as a number can get assigned a character thing. You can generally not do that in C and C++. Variables must be declared. They must have a type before you can assign. Types are sort of things that are similar to what we have in R, with a bit more variety. There's signed and unsigned. Floating point numbers come in high and lower resolution. This only really mattered 20, 30 years ago when computers were smaller. These days we're basically always using this. There's a logic vector. There's sort of isn't but is something for standard for strings, a standard type that everybody uses. All variables are scalars, so everything is 1 unless you use standard vector around one of them, so you have to do that. And you can do composite types as classes and structs. Control structures are very similar: for loop, while loop, if, switch. Functions are similar, but it's positional matching only, not by arguments. There's something about pointers, we'll skip that. I'll just fly through this as well. That's a minimal example of how we would have a structure. We can have a structure embedded in another structure. The next thing that you can do from a structure to a class is that you have the storage and then functions accessing it. So the canonical examples always are setters and getters. Not really to get into this, because you'll need more time to, if you're completely new to this, to learn C++ or brush up on this. But this would be an example of a class structure hiding data, sealing it, making it a safer design. Because when you're representing a date this way, you can't, from the outside, access year, months, and date in any other way but by these setters, because they're declared private. So that's sort of something you can do. This is the thing about the STL. I just mention that because some of our interfaces are set up to resemble these, because that has benefits for other access functions, other summary functions, other compute facilities offered by the STL. One way to get through loops is with these iterator things. So this is one way how one would use begin and end. An iterator knows that it's on a position, so you just augment the iterator to get to the next. And that's how you would get from the beginning to the end. Just understand that that's there because we need that for things like this. So this would be the C++y way, not knowing R at all, how you would calculate the sum of a vector. You may have a structure, a vector or a list called S, because it's an STL type that are generic, so that independent of the representation, the functioning is the same. So you always get a begin and end iterator, and then you can, with that, call something called accumulate that you initialize as 0, and this would then traverse all the elements from begin to the one before end. That's the convention, and sum them all up. So accumulate is sort of common as find, count. Transform sweeps through and applies something for each inner product and sort of stuff like that. But just in template programming you need, because the typed languages require a specific type, but we don't really have time to go over this. But that's what something like that looks like. You just say basically this will be generic of a type T. It returns a T, takes 2 T's, and this is sort of a something carried over from old C. It's what we have in R with an if-else. It basically just says if Y is less than X, then return Y, otherwise return X, and hence it's an implementation of a min. And when this is actually needed in a program and you instantiate, say, with int and double, then you get real instances created of that. Anyhow, similarly here an example of a templated square function that you can sweep through with transform from begin and end. But again, we're not having a C++ course this morning, so maybe just hold on to this one. The books by Myers that I mentioned are great. Your public library or university library will have that. So does a bookstore. They're not that expensive. This one's even cheaper because it's free. That's from a Dutch academic. It's huge. It's sort of 1,400 pages in either a PDF or on the website. Some Linux distros has a package, so I know you can apt-get install it. It's not a bad book at all. There's an FAQ, actually 2 of them for C++, the full version and the light version. And these are links to, I sometimes forget about that, to when you're in Stack Overflow and things are tagged, there's a tag for C++ as well, and then there's meta info on the tag. And sometimes people go in and provide really, really good resources. This thing is a complete stunner. That book list just sort of goes on for pages and pages, and it's blocked. If you're a complete beginner, sort of here's 10 good books. If you know a bit more, here's 10 of them, and sort of the Maya ones are there too, and lots of links and info that's updated to tutorial. So that's free as well, and there's worse places to get started with. So, and then another thing, as we're going sort of over tooling and the things, so how do you get out of trouble when you're in trouble? And that's still hard. There's no general answer about how to do debugging well. You know, in R, it's easy-ish to step through with the debugger. You can do that too, but you have to learn a bit about the debugger. If you don't want to do that, you know, putting printfs in still helps somewhat. There's extra tools. You may have heard about these. Cran uses them for testing as well. So Valgrind is one that finds when memory gets allocated but not freed, so-called leaks. It, I think, also finds when you access in regions of memory that you haven't actually reserved, but that's a speciality of also these things. The newer compilers, newer versions of G++ and Clang do that. That's address sanitizer and undefined behavior sanitizers, ASAN, UBSAN. Sadly, in order to use them, you have to build your versions of R with them. So that's a bit of extra work we don't always want to do. But what's really helpful is sort of Docker containers that do that. And Gabor's RHub also has that too. So you can just push your package up sort of into the cloud and get them analyzed by that. So that's good to know. And then finally, if you haven't already, get into the habit of using version control, because you get back to sort of previous versions and you can compare easily. And I really think that having a good editor works. So that was all the preliminary. And then one thing that once you really want to get going and you reason about, well, you know, how do I do this and that? Let me just jump to that real quickly. That was another great idea by JJ. So we set this up, I think, at the end of 2012 or so. It's a website that physically lives on GitHub. And if you go sort of from the bottom up, I think it no longer shows all of them, but just the top 100. So now we have a bit of 100. So you see from 2013 to, you know, all the way this year. It's various topics. There's a bit of a word cloud here, and then you can sort of, you know, if you want to ask about something, and I think this is something that we'll get to in a minute on one of the slides, you can just say, well, how do I do a subsetting? And then it comes back, and within, so it's a, what's that called? It's a customized Google search, or parameterized Google search. It just looks on this website. You get to particular topics, and then each of these is a is sort of a short knitted document with code and output. And each of those, just with the click of a button, you can actually get. You can, of course, also clone the entire repo. And that's a really good place to go back and sort of recall, well, how is this again done? Or if any of you come up with a particularly clever way of computing something new with Rcpp, submit it as a story. We have a page there about, you know, just how to do that. It's really easy to send out a pull request, and then you have your piece on it too. So gallery rcpp.org. And I'll just go there and start with a few examples. So that's the URL again. It's over 100 ready to run and documented little stories. It's like a blog or Jekyll site. And you can get the whole thing or pieces one by one. And sort of simple examples. And I'm going to show you 3 different ones because it helps us sort of to get familiar with one particular example. So this is something really simple just to study it. We don't really have to do it because we have a perfectly fine CumSum function in R itself, but sometimes we just want to start with something simple to get our feet wet or get a working example of something. So this would be in a complete file that's then sourced. We get to, I think, how that's done too. What one needs here is one header line that introduces everything that Rcpp provides in a single line. So you only ever need that line. For the not for this solution, but basically in the same file for what comes after it, the next solution on the next slide, we need to include numeric from the C standard library because we will then also use partial sum, but that's not here. Next thing is we're using a namespace shorthand so that things that come from Rcpp don't need to get prefixed by Rcpp : : That just means that everything from this namespace is now imported. Very similar behavior to what we have in R now with namespaces. So numeric vector is an Rcpp thing. Then how do we calculate a cumulative sum? Well, we get a temp variable, an accumulator that we set up and initialize at 0. We generate ourselves a new independent result vector res of the same size as x. And then from 0 all the way to the size of the initial vector, we augment the helper variable, the accumulation, by the value of the current element. So in the first iteration, it's the first element, in the second one, the first of the first two, and so on. And at each element, assign the current value of that. And that way, we're filling the result vector with the sums up to that point at each element, and then we return it. So nothing too terrible, 6 lines. Using the STL, which again has this sort of generic behavior, makes it a little easier because now we're getting it vectorized, albeit vectorized in a fashion that doesn't yet read all that natural to us as R programmers. But now it's just basically 2 statements in the return. Again, we're reserving a results vector. We're sticking the results vector in here as the third argument to partial sum. And otherwise, we're saying begin to end, work over these, and then we're just basically saying we want the sum of all the elements comprised between begin and end. And we've seen that with the other ones before, so the way that works with the STL is always, it's basically square bracket on the left, including that element, and round paren on the right, all elements up to but not including end, because by this convention, C++, the end iterator is basically the one after the last element. So you can always traverse it till your iterator hits the end element, and that one you no longer want to process. And that's the same convention from here to there with the results stuck in there. So now we get a cumulative sum without having to loop because the library does that for us. And that's then a sort of a nice motivation for introducing what we called Rcpp sugar, which was a really clever idea by Romain and has become really, really popular because now we can do things in Rcpp. Because we have them implemented, they made them available, but you can do the same, that basically look and feel the same way they do in R. We go in with the vector x, and we just say CumSum. And then it's understood that for a vector going in x, we get a return vector, and basically the internal implementation of CumSum does any one of those things we've seen on the 2 previous slides. And that, we can play with either by retyping it, or if we're in the repo, where am I? So I used the same account last week in Zurich, so there were some other directories flowing around. But suppose I had just cloned. Actually have a project for that? Yeah, exactly. That's a very good idea, thank you. Yes, absolutely. Hold on. I was just... that would be, wait, where is that? Is that not in view? It's somewhere here. It's just Shift Control Plus or something, right? And there we go. How's that? That's better, right? Better for everybody. Otherwise, just holler. I mean, you can just do it sort of one more. Speak up, please. More. Yeah. So, how's that? Good. All right. Let me pretend this one wasn't here. That's another good trick. So let me just say. So I showed you this. Let me make this a little bigger too. So there's a repo, and I can just go here. Forget the fact that I actually have, of course, keys to this repo. So I just say HTTPS read only. I copy this. Then in RStudio, one thing that's pretty good and which more or less all RStudio versions for the last couple of years support. I'm a bit in the habit of living at the edge and getting a reasonably new one. This one that we have on this server too is newish too, but I'm trying hard not to show you features that not all other versions have. Otherwise, if I do so, you will find this at dailies.rstudio.com. So if you go to version control and then say, yep, I have a Git repository in mind, and then paste the URL in. I just pasted what I had copied from here. Where's the copy symbol? Copy, paste. Now it sets this up. And exactly, let's just put it here. And if I then say create project, it actually goes out, does a git clone, and I get a brand new repository, nothing else in there with just what's there. And that just happens to be the project file in the examples directory. So, and then I can go in and I get all these examples that we have in these slides, as well as in the slides that I clip, but that are in the slide deck for Zurich. So this is now the exact same thing that I had on the slide, and then I can just say, source me this thing, and source in the IDE means it knows what to do, and it invokes source CPP from Rcpp, whether Rcpp is loaded or not. So obviously, when you do library Rcpp, then you can do it without the prefix. And the cool thing that happened now is what I had mentioned earlier. This thing here is a function CumSum1 that we wrote. In the first examples that I showed you with CPP function, we just submitted it as a string. Here we're sourcing it. With the sourcing, there's a slightly different convention. We're now using the convention that if a function, so this is a C++ function from curly to curly, returning a numeric vector, having the name CumSum, and taking a numeric vector. If that function is preceded by this tag, square bracket, Rcpp export, which is behind a comment character in C++, so the compiler doesn't see it, but our tooling works with it. And this is basically an annotation, if you wish, that we say we want this function callable from R. If goes the other way too, so that means now I have function CumSum1, CumSum2, CumSum3. If I break this regex, just putting spaces in here, and explicitly remember everything in R is an object, so a function is an object, so I can delete the function. Now I only have CumSum2 and 3. See that? One disappeared. If I then either do cursor up here or hit the source button again, now compile and source the same source file again. Yeah. It's cached, and let me think now. Why is it tricking? Yes. Thank you. Which is very good. See, I hadn't done this. There's always two ways, one of which may be worse. Yes, see now the behavior is, I hit the source button, it actually saved it on default, and now it recompiled the new version and the file isn't there. So you have the option of having functions in your file that are not visible, just how in an R package they have the opportunity of having files that the namespace doesn't export. But the converse is also true. You could have an error here. The tooling is actually so clever that if you source CPP a file, Rcpp knows you're doing that for a purpose. You probably want to give yourself an R-callable function. If the file contains not a single export tag, you actually get a warning message. Sure, I just compiled this file for you. You're writing good code. It didn't even have an error. I didn't have a symbol for you. Did you really mean that? It's not quite that verbose, but that's basically it. How does something like, oops, where's my cursor? Wrong spot. How does a function like this look? It's actually not all that interesting because it's basically a wrapper that goes off calling something that's compiled code behind the scenes. But so it's worth sort of stopping here, looking at a few things, trying a few things. So for example, if I now say comes, crikey, where did I just type? Come some 1 to 10. I think that gives me 100. Oh no, okay, right. Thinking of the prod. That was the first variant. By now I have several. We can't all see them at the same time on this resolution, but just on the slide, there's the two other versions. I can ascertain that they're all the same. I could even do that programmatically if I didn't really trust my programming abilities. Took me a couple of years also to understand and appreciate that all equal takes more than 2 arguments. It doesn't compare just a pair, but it compares sort of any number, and we see, yep, they're all sort of good. What I sort of had said, when we're writing these things for the first time, sort of how do I debug? Well, we just may put print statements in. The R manual really recommends that we're using the R facilities, so I'm using rprintf rather than printf. If we're just writing code for ourselves, I could also use printf, but cran checks actually prefer it that way, sort of new line in here, and then I can say I and X, so that's printf, similar to Rprintf, sort of standard feature, and if I do that, we see, oh yeah, right, very good. Good environment. So I inadvertently made a mistake. I forgot the semicolon. One difference between R and C++ is they all have to finish on a semicolon. And the error that I got was spot on, but not only was I not buried between a whole rest of other error messages, the one succinct one in there was being taken, was analyzed, and my cursor was basically put right on the spot. So now let's do this. Let's do this again. Now I don't get an error. It takes about a second to compute this, and if we then invoke this, then we get our intermediate results when we're debugging. So that's kind of cool. Another thing that we don't, really have time for today, but I'll just show you in brief. Sort of one thing that's really nifty is, because we're building this with Rcpp attributes, and there's code being written for us behind the scenes. That code actually embeds the whole structure in a try-catch block. So what happens if I try to calculate a cumulative sum of a function that I have defined as a numeric vector, and I say A, B, and C? Will that work? Not really, but what happens is controlled. So what happens is, of course, for R, this is a perfectly well-defined vector. It just happens to be a character vector. And when you stick a character vector into a numeric vector, it kind of just says, nah, can't do. I was expecting numbers, you were giving me text. So the instantiation of the object knows it's in an error condition, and what then happens is, at that level, we're throwing an exception but because all the code generated this way has a try-catch block around it, that means that the exception is actually intercepted, caught, and the text of the exception is turned into a proper error message. So instead of, say, blowing up here, the way it might have been when we wrote really bare bones C++ interface code to R without that layer around, the thing may have gotten, into some sort of undefined behavior because, hey, a character vector really doesn't belong in a numeric one. But now it just says, oh, actually, hey, we just made that better a couple of months ago. Actually, that was James's contribution. I was just looking at it, looked unfamiliar. Not only does it say, okay, you called me with the type that doesn't work, now it's even more expressive because it says you came with a character and I expected a double. So that's kind of nifty. Another one that's also cool is, so it's sort of trick question for, well, not trick question, sort of intermediate R question. Anybody know what this is? What's the type of this sequence? It's integer because the colon makes the sequence integer. You don't want a sequence of doubles typically, whereas if I just say 1, which is one of the ones that I use in the sequence, that's actually a numeric. So 1:5 is pretty much the same as saying 1L, 2L, all the way to 5. So what that meant in passing was we actually did call this all the time with an integer vector, and that's just standard behavior in C and C++. Ints cast up to doubles transparently. But that doesn't mean that characters become numbers transparently. So you can go from whole numbers to floating point numbers because that's a superset, but nothing else. So anyhow, so error condition handling is sort of kind of good. And I think that's the main thing I wanted to show here. We could now benchmark between the three solutions and do other tricks, but let's just, with that, now that our hands a little bit dirty, let's just carry on. This is a really powerful helper that's fascinating and that I think is good that I show you here because it gives me an opportunity to point it out and also make clear that it does certain things but not others. What we're doing here is that now in the interface, CumSum just took a vector. Now we're taking a function as well as a vector. So what we're basically demonstrating is that we can take a function that's defined at the R level, pass it down to the C++ level, and have it evaluated at the C++ level. That's sort of an existence proof style thing that any R function you have, you can also get to from Rcpp, from C++, which is tremendous for things like, I don't know, getting initial values with a helper function that web scrapes, getting initial values to instantiate your simulations from a database, doing a lot of things that would be really expensive, difficult, time-consuming, boring, you name it, to redo in C++. You can do them in R, but there's one thing, of course, that this does not do. This does not execute your R function at C++ speed. So just because you can execute an R function does not mean that you leave R behind. It's still an R function. Don't do this in a iterative ML estimation, in an iterative gradient descent optimization. Evaluating an R function is still expensive, so you don't want to do that inside your loops, you just want to do it on the outside. But the mechanic of it could not be easier. We just say function f and it's a function f, and hold on, I don't have an example slide. So then that's worth just hopping here. So R function from C, because this one probably has one. It just didn't survive to the slide. I bring this one. This is literally the file from the gallery. So you see the way we've implemented that is the markup on the slide is sort of a lot of text, and then here I'm saying set seed, get a normal vector, and I take a function 5num. 5num is a really old function by John Tukey, which is sort of a predecessor to summary, if you wish, because I think it gives you min, max, first quartile, median. I should really know that. I just used it here because it's concise. It takes a vector and gives 5 summary numbers back, and we can take the same thing from from C++. So now I'm just going to source this whole thing because it's, it's still a C++ file. And the thing that happens when I source a file, that's another meta tag that we have here. So this, what you saw above there, is C comment rather than C++ comment. C comment always is /* all the way to a closing */ which can be multi-line. When we do /* followed by 2 stars, a space, and R, it's another meta instruction for us. That means after we've transformed this file into the C++ code that it contains, please execute me the R code in here. So you see, line 36, set seed 42, line 37, x equals R norm 1e5, 5 num of x, I get these numbers. And then in the rest of the file, I have exactly the same code as on the slide before. And then here, if I do this, so I pass 5 num down to my not all that interesting C++ function, because all that it does, it takes f and x and returns f on x, but it clearly shows that it gives us the same result back. So we passed a function down, and that can really be anything. It can be much more complex that you have yourself. So if, for example, I do call function x, or actually there was a reason. I think I can't do this because it gives me a named vector back. And no, this works the same way. So could have used summary instead of 5 num, or and I think this one, right, because it also has default arguments. So all good, because it just gets evaluated. So perfectly generic. We can call R function from C++, but big finger wagging, but they don't get any faster. Let's do one more, and then while we're in the middle of that, then we at the proper time do our coffee break. Subsetting. For the first years, we didn't really have this. Because it required extra code, but sort of now we do. So you can now, for a given vector x, subset on Booleans just the same way you can in R. So if you go in, say, with a vector, a big N01, where there's some negative and some positive, this would give you the reduction to only the ones that are positive. So Boolean expression permitted as an indexing vector. Similarly, just how you can in R, you can index by position. So if you have a really long vector and you want elements 23, 46, and 99, you just create an int vector with those positions and you get that back. And lastly, if the vector is named, as for example what we got back from quantile or summary, then you can also pick them up by the name in there. And of course that will end in tears in an error condition if you try to subset by name on a vector that has no names. But if they're there, you can do that. And that works on vectors, lists, all those other things. I will get to my favorite math package, Armadillo, after the break. But that's just related because historically, before we rewrote that, we always pointed to ARMA. Here's how you do it on ARMA. And that gives you a first flavor that sort of between different packages and libraries, the conventions may be different. So here I'm coming in with a matrix. And I'm creating myself a transpose of that matrix. And the logical condition here is I want all these, it's element by element comparison. I want all the elements where the transpose is larger than the element at the position of the transpose is larger than the element in the original matrix. And because Armadillo, as I'll say later, sort of aims at giving you a replacement for MATLAB, it's really numeric. It only does ints, doubles, and complex, but it does, and so no Boolean, but it does them as signed and unsigned. So Conrad's convention is that a logical expression just gets stored as an unsigned matrix, and you can then transform from an unsigned matrix to a normal matrix, because in order to send this back to R, we need a normal matrix. R only has ints and doubles, and not unsigned, so we have to do the conversion. So that's just the subsetting, that's one, and the other one is you can also do it on conditions, just we had it over there. So if I compute Z as the product of M and its transpose, and I want to find all the elements of Z that are larger than 100, then this gives one of these element subsetting suitable types back that you set into LM, and then you get that back. Full worked example on the gallery page for subsetting, and I think with that I should probably break, and if I have that right, we have half an hour. Is that correct? Yeah, good. So then let me log this one. We all refresh with coffee. Hit me up with questions in the break if you want, and otherwise we will resume here in about half an hour.